This is a finalization of Chapter 13. So what I wanted to go through real quickly on Chapter 13 to finalize it. I know we were finishing it up about, I think it was 2 weeks ago, but things happen, so let's continue on and finish it up. This is the finalization of Chapter 13. So I'd probably do a little bit of a review for you, but if you need any help or any questions on that Chapter 13, please just outreach to me. We actually went into talking about Gauss and Maxwell's equations and Lenz's law and stuff like that, but we'll get into a little more on Lenz. But let's pick up where we left off before in Chapter 13, and this is actually, I think it's on close to 13-5. So when you look at a magnet itself, we know that magnets, all magnets have two poles. We know that from the rings. There's a north pole and a south pole. So we know there's a north pole and a south pole on it. Well, what we want to do is, if it's a permanent magnet, if we have some permanent magnets, what we want to do is we want to keep this permanent magnet from losing its magnetic strength. So in order to do that, this is what we call in the book, they call it a keeper for a magnet. Basically on this, so if we actually take a look at a magnet here, let's do a horseshoe magnet here a little bit. And let's do it this way. And let's say that we are going to be storing some magnets. And let's say that this is the south pole and this is the north pole, and we get a horseshoe magnet. So basically what we need to do is we want to keep the strength of this magnetic field, and this is what they call keeper for a magnet is. So basically what this principle behind it is, we want to keep the magnetic field from actually collapsing. So what we actually do is, remember when we said that like poles will attract and unlike poles like poles will repel and unlike poles will attract. So basically if we take and we do this, and we take another magnet just like it is. Remember, these are permanent magnets, and I'm leaving a little gap there, but there's really no gap there. So basically, if we do something like this, and these would be attracted, and basically the magnets will come together, right? So basically, the principle behind this is that what we do is we keeping the magnetic field from actually collapsing over a long period of time. This is what we would do if we're storing magnets, when we're storing some magnets. So that's what they mean for a keeper for a magnet. All right, 13-6 actually goes over the types of magnets we have. So 13-6 actually we talk about the types of magnets. There are actually two types of magnets. One's called electromagnet, and the second type is what they call permanent magnet. So electromagnet is, let's talk about electromagnet is a magnet. So electromagnet is a magnet that actually uses electricity in order to create the magnetic field. So electromagnet uses electricity to create a magnetic field. So if we're going to use if we're going to create a magnetic field out of for electromagnet, what we need is two things. Number one is we need an iron bar. Iron is probably one of the best materials for creating electromagnet. So we have an iron bar. And then what else we have to do is we have to wind this thing up. So we have to use some what we call enameled wire. So I know this is going to look a little strange here, but this is my drawing. So basically what you do is you bring around and you continuously bring around wires. And these are going to be finely tight together. So these are going to be tight together. But what we need is an electromagnet. What we need to do is get a source of energy. So what we're going to do is, this case is the battery. If I move that up, now you can see it. Sorry about that. So we have a battery. So this is the positive and this is the negative. So there's two types of electromagnet and a permanent magnet. Electromagnetic, it uses electricity to create a magnetic field. So basically the theory behind this is, if we take this and we take some enamel wire and wrap it around some sort of iron bar, and let's say the number of turns is equal to 100, we would actually, and these windings would actually be very close together, and we apply a battery to it, we would create a magnetic field. So this magnetic field would be created, and if we look at it and we use the the left-hand rule and we point in the direction, we take our fingers and wrap it around the direction where windings, the thumb would actually point in to the North Pole. So if we do that, there's north and there's the south. The other way we can actually identify it is the positive, usually it points to the North Pole on it. So the more turns, so let's write down some facts here. So number one is we need thin wire. Thin wire, so we're looking at a number 24 gauge, or we could use actually we could use anything, but number 24, number 20, let's say number 26 gauge would be a good example. Other gauges could be used depending on how much current you're going to draw too. So you go down to 18 gauge, but the point here is that in order to create a magnetic field, you use a DC. In this case, we're using DC battery. The question is, could you use some sort of AC? Well, we'll talk about that a little later on when we get into inductors. So basically, this is the basic circuit of it. So what you have here is you have some windings. They're really going to be nice and tight together. So if we're looking at this, we really want all these windings to be nice and tight and nice and even too. We don't want anything to start bunching up. That way, we're creating a nice magnetic field. The flux lines are nicely aligned, everything's good. So the more turns, so we can put down number 2, more turns equals stronger magnet. Okay. Permanent magnet. A permanent magnet. Basically what it says, it's a permanent magnet, but there's two types of permanent magnets we can actually have. One, you can create a permanent magnet using the manufacturing process, and the second way is we can actually use a permanent magnet and we can actually get it from the Earth, and these are Earth type of magnets, which are neodymium is a good example. Very strong. These are very strong magnets. Very strong magnets. A good example in the book says it uses cobalt steel during the manufacturing process. But again, the biggest thing here is it's a permanent magnet. Well, a permanent magnet, if a permanent magnet is really strong, what can we use these permanent magnets? Well, let's step back and look at electromagnet. We use them all the time, you just don't realize. A good example is a solenoid. A solenoid in a car, your starter in your car. Another good example of an electromagnet is actually could be the electromagnet can be the taping, the old, well, they call VHS tapes, where they have some magnetic material on it. So now a permanent magnet, like I said, is neodymium, and then you can actually make them. A good example of a permanent magnet would be a speaker. We use the speakers all the time. Another good place for these permanent magnets are you find them in hard drives. So that's what a permanent magnet is. So there is two types of magnetic materials we actually look at. So ferromagnetic materials. So there's ferromagnetic materials. These are the permeability is greater than say it's greater than 5,000. That's basically iron, steel, nickel, cobalt. And then you've got a paramagnetic, which is aluminum, platinum, manganese, and chromium, and it's less than 1. And then you got diamagnetic. These are bismuth, antimony, copper, zinc, and a few others. Permeability is less than 1. I'm going to rephrase paramagnetic. Sorry, is greater than 1. So I made a mistake on that. So shielding. When they actually talk about shielding, it's preventing one component affecting another. A good example of shielding is a lot of times we want to do is prevent magnets actually from erasing the old hard drive. So we have to shield it. That's a good example of it. So shielding is preventing one component affecting another. So another good example is, how about we have copper cable? We use the copper strands, the braid on it is actually moving. So what it does, it actually protects the copper cord that's inside there from interference from noise, such as lights, fluorescent lights, motors, etc., like that. So, and then, so I'm going to just, and then finally, Hall effect. This is actually something that's new, and we actually would do a lab here. A Hall effect is a small voltage generated across a conductor. So basically, the Hall effect is just started up about, it's been just about, I'd say, the last 10 or 20 years. So, but basically what you're doing is you're using a magnet and creating a Hall effect field. So remember, a magnet creates a magnetic field. Well, there's a sensor in there, and it's a semiconductor material that's sensitive to this magnetic field. When it detects it, it creates a voltage, and well, we could create a Hall effect. That's what we call a Hall effect. Relative permeability, the ability to concentrate a magnetic field. So if you ever hear of the relative permeability, that's the ability to concentrate a magnetic field. So this concludes Chapter 13. If you have any questions on Chapter 13, please feel free to contact me. Thank you.